Okay, the main point of this video is looking at finding the gradient of a line using this formula here, m equals tan theta. Before we do that, we're just going to look at other ways we can find the gradient. So we know from in year 9 and 10 that to find the gradient, we just use rise over run. So we use any 2 points on the line and rise over run. Or we could do it this way. This is the run, that's the rise as well. So it would be rise over run. So rise over run, this obviously has a positive gradient. And here, the gradient, you just pick any 2 points on the line. Gradient is rise over run there. However, some people may run first and then rise, but we always do rise over the run, okay? So just with this idea of picking the 2 points, you can also use the formula. If you've got 2 points, you can find the gradient of a line using the formula, which is y2 minus y1. So gradient m is given the symbol m is y2 minus y1 over x2 minus x1. Now that's if you've got the points x1, y1 is your first point and x2, y2 is your second point. So this distance here is the difference in the y values. That's where the y2 minus y1 comes from. And this distance here is whatever x value you've got here minus the x value here. So that bit is x2 minus x1. So again, this formula here, y2 minus y1 over x2 minus x1, is really just rise over run. So it's the rise divided by the run. Now we're going to take that and look at that again using trigonometry. So let's say again we've got 2 points. Here I've got point 2, which is x2, y2, and here I've got point 1, which is x1, y1, okay? So you can't see that very well. Okay, now we know the gradient is rise over run. But this rise here is the same as this here, okay? So what I'm doing here, I'm actually drawing up a right angle triangle, but I'm doing it downwards this time instead of rise over run. I'm doing the run first and then the rise. This is a horizontal line, and this line is parallel to the x-axis. So if I put here, theta is the angle that the line makes with a horizontal, then the line also makes this angle theta also with the x-axis. So these two angles here are the same, equal in magnitude, because they are corresponding angles on parallel lines. So if this is a horizontal line and so is the x-axis, if I draw this line, it'll eventually cut the x-axis. So the angle that this line makes with the x-axis is theta, but I can draw a triangle between any 2 points here, and that angle there, the angle from the positive x-axis, so this is called the positive x-axis, that angle is also theta. Now, we know from trigonometry that tan theta equals opposite over adjacent. But if we look back at what this distance here is, this is the rise. This is the rise, this is the run. And we know that the rise is y2 minus y1. So this distance here is opposite side to the angle, but it's y2 minus y1. And this side here is adjacent to the angle, but we know its distance is whatever x2 is minus x1. So we know that the gradient is y2, minus y1 over x2 minus x1. But if we put this angle theta in, we know that this y2 minus y1 is the same as the opposite side relative to theta, and the x2 minus x1 is the adjacent side relative to theta. Now we know that opposite over adjacent is tan theta. Hence, that's how we get the formula that the gradient of a line is tan theta. Okay, now I'm going to give you an example, not one that you would normally get, but just showing why and how this works. Now, let's say I've got this line here of y equals x. Sorry, I haven't drawn it very well. This is the line y equals x. So I'm just going to do 2 points on the line, for example. This might be the point 1, 1, and this might be the point 3, 3. Now we know that the rise will be 2 and the run will be 2. Now, actually, I need a horizontal line with the x-axis, so I'm going to draw my triangle. So if this is theta, I'm drawing a right angle triangle here, because always when we use m, if I want to find the gradient of this line using m equals tan theta, theta is the angle that the line makes with the positive x-axis. I'm just picking any 2 points I know on the line. So I know that this distance across here is 2 and this is 2 and this is a right angle triangle because they're at right angles, the horizontal and the vertical line. Now, you would already know if this is 90 degrees and this is 2 and 2, then this is an isosceles triangle. So these two side lengths are equal, which means that we've got 45 degrees there, okay? So theta should be 45 degrees, but let's have a look. If we say that m is tan theta, now tan theta is opposite over adjacent. In this case, it's 2 over 2. In other words, the gradient is 1. But we were saying that we think that this angle here, we know because it's an equilateral triangle, that these will be 45 degrees. So let's just see what the tan of 45 degrees is. And that is also 1 from our exact values. So we can see that m is 1 and tan 45 is 1. That means that the gradient of this line is tan of 45 degrees, which is 1, okay? So gradient of the line is tan of 45 degrees, which is 1. So that's just a simple example just showing you. It's not the type of example you would get, but it just shows you how example we've just looked at is where the gradient, so we said that this angle here is 45 degrees. This is an acute angle, and we know from all stations to central that, remember all stations to central, that sine, cos and tan are all positive in quadrant 1. So tan of 45 would be positive. So anything from tan of 1 degree up to tan of up to, but not including tan of 90, so say tan of 89, is all positive. So you would get a positive gradient. We can see here that the gradient's positive. But, however, we do sometimes have negative gradients. Now I'm going to use the line y equals negative x, just as my example. So if this is the line y equals negative x, I'm just going to choose some points on the line. I'm going to actually choose the point 0, 0 and maybe the point 3, 3. Okay, now, we know that the gradient, if this is y equals negative x, the gradient of this line is negative 1. I know, for example, that this distance here is 3. If this is the point 0, 0 and this is the point 3, sorry, not 3, 3, it would be negative 3, 3. Okay, that this distance here is 3 and this distance here is 3. Now, this angle here, though, this angle here is 45 degrees because it's an isosceles triangle. Okay, so we've got 3 and 3. This is 45 degrees. But remember, when we use m equals tan theta, theta is the angle that the line makes with the positive direction of the x-axis. So what I'm going to do, I'm not going to call this theta. I'm just going to call this alpha, for example. If this is the angle alpha, then this is the angle theta. Now, if this angle here we know, so if alpha is 45 degrees, and we know that, then theta will be, so this little angle in here is 45 degrees. Theta will be 180 minus 45 degrees because remember, theta is the angle that the line, this line makes with the positive direction of the next x-axis. Now, what we mean by positive direction of x-axis is as follows. This is all the x-axis. But for example, these are the numbers positive 1, 2, 3. These are the numbers negative 1, 2, negative 1, negative 2, negative 3. So this is the positive direction of the x-axis. This is the negative direction of the x-axis. So the angle that this line makes with the positive direction of the x-axis is this angle here, which is 135 degrees. Now we all know that the gradient of this line is negative 1 because when you use y equals mx plus b, the gradient is negative 1, the coefficient of the x, okay? So let's see what the tan of 135 degrees is. Now you can use your calculator, or from exact angles, we know that that is the same as negative tan of 45 degrees, which is negative. Now we know that tan 45 degrees is 1. So remember, we do know that this line has a negative gradient. All right, we can see. But if it just happens to be 45 degrees is the example I chose because we know that tan 45 is an exact value, all right? If you do tan 135 on your calculator, you get -1, or we can do it by using the acute angle in quadrant 2 is 45. So therefore tan 135 is the same as negative tan 45, okay? Which is -1. And so therefore, for acute angles theta, m equals tan theta is positive. So where, sorry, I don't have to put my axis there. I'll just do it over here. So where, remember this is the positive x-axis, where this angle is acute, tan theta will be positive, and that represents our positive gradient as well. And for obtuse angles, m equals tan theta is less than 0. Oh, sorry, that's not a very good line. That's meant to be a straight line. I know it doesn't look like one, but it's meant to be one. Sorry, that's meant to be theta. So if I did tan of this theta here, that would give me a negative value because we can see the gradient of this line is negative. From exercise 7.3, find the gradient to two significant figures of a straight line that makes an angle of 42 degrees 51 minutes with the x-axis. It's with the positive x-axis. Okay, so for example, we don't know what the line is, but the angle that it makes with the x-axis is 42 degrees 51 minutes. So therefore we know that the gradient is m equals tan theta, which is the tan of 42 degrees 51 minutes. Okay, we know that that would be a gradient, it would be a positive gradient, we know that, and the gradient should be a little bit less than 1 because we know that 45 degrees would give us a gradient exactly of 1. Okay, like we looked at in the examples, the gradient would be 0.93 to two significant figures. Okay, now going in the reverse direction, this question here, find the angle in degrees and minutes that a straight line makes with the x-axis in the positive direction if its gradient is -2. So let's say we have a line, doesn't matter where it is, like here, and its gradient is -2. We want the angle that the line makes with the positive direction of the x-axis, and we can see that this line would be, it's got a negative gradient, and this angle would be an obtuse angle. So we know that m equals tan theta. So the gradient is -2, so -2 equals tan theta. So that means that tan theta is -2, and so now to work out theta, because tan theta is negative, remember with all stations to central, okay, all stations to central, tan is positive in quadrants 1 and 3, so tan will be negative in quadrants 2 and 4, and an obtuse angle is a quadrant 2 angle, and tan is negative in quadrant 2. So to work out what theta is, you just work out the acute angle theta first, so we don't put the -2 in on our calculator. So we go, acute angle is tan to the -1 of +2, so shift tan of +2, which is 63 degrees, and I'm going to do this in degrees and minutes, so just doing that again, shift tan of 2, 63 degrees 26 minutes is this acute angle. So tan of theta, if you do inverse tan of 2, you get 63 degrees 26 minutes, but we can see this is an obtuse angle. And so quadrant 2 angles, we work them out by doing 180 minus this angle, 180 minus 23 degrees, 63 minutes. And we get 106 16 degrees 34 minutes. If the line is positive, you can just use tan theta, all right? But if the gradient of the line is negative, as in this case here, and you're given the gradient, you have to work out the acute angle first and then do 180 minus, okay? Otherwise, you will notice that if you've got tan theta is -2, and if you write, well, theta is tan to the -1 of -2, you will get negative 63 degrees 26 minutes. So when you get that, that is the negative angle that it makes with the x-axis. That's actually this angle. So positive angles go clockwise and negative angles go anti-clockwise. So if you don't put in just theta is inverse tan of 2, you will get negative 63 degrees 26 minutes, which is this angle down here. All right, so if you want this angle up here, it's 180 minus that. All right. When he says find the exact value of x with a rational denominator if the line passing through the point x3 and 2, 1 makes an angle of 60 degrees with the x-axis. Now let's just have a quick plot here. So if we've got 2, 1, that's 1 point. Now if you want an angle of 60 degrees, roughly the line's going to go like this. This should be 60 degrees. And the other point we've got is something x3, okay? So if this is, 2, 1, this is x3, probably should be a little bit lower here, down here. Yeah, 2, 1, x3, sorry, no, it's a height of 3. So this is 2, 1 there, and x3 would be roughly about up here. So this would be the point x3. Right, we want the value of this x. Now it does look like this value is, it has to be bigger than an x value of 2, okay? So let's have a look. We know that m is tan of theta. So the gradient of this line is tan of 60 degrees. Now from our exact values, we know that tan of 60 is √3. So the gradient of this line is √3 from exact values, okay? Now, let's just do up our right angle triangle. Okay, so we know that this is 60 degrees. All right, so we know that we've got the points 2, 1 here, and this is the point x3. Okay, so we know that the gradient of this line is also y2 minus y1 over x2 minus x1. So y2 minus y1 is 3 minus 1, and x2 minus x1 is x minus 2. So that's 3 minus 1 is 2 over x minus 2. Now we know that that gradient, 2 over whatever x minus 2 is, that's equal to √3. So therefore we can put, we've got two equations here, m is tan theta, and the gradient m is 2 over x minus 2, so we can put those equal to each other. So therefore 2 over x minus 2, equals √3. So therefore, solving this equation, 2 equals √3 bracket x minus 2. In other words, 2 equals √3 x minus 2 √3. And just rearranging this and making x the subject, 2 plus 2 √3 equals x, which means, equals √3x, And so therefore x equals 2 plus 2 √3 divided by √3. Okay, so that is what the exact value of point x is, and I could factorize that as follows. So it's 2 bracket 1 plus √3 over √3. So that is the exact value of what x is with an irrational denominator. So therefore, to rationalize the denominator, I'll just multiply by √3 over √3 here. Just get rid of this, which is 2 √3 plus 2 √3 times √3 is 6, which is because it's 2 times 3, over √3 plus √3 is 3. So therefore, x is 2 √3 plus 6 over 3.